Okay, welcome back to really the beginning of our forces unit in earnest. And we're today going to talk about why objects move. So far, during the kinematics unit, we discussed how objects moved. We discussed describing their distance that they move, displacement, their speed or velocity, and their acceleration. We talked about describing motion. We didn't talk about why objects have that motion in the first place. So the basic question boils down to, why do objects move? There's a very obvious answer to this, but I think that obvious answer is useful. Objects move because something influences them so that they move. We kind of have alluded to this in the past when we talked about free fall. We said that free fall was a type of motion in which the only influence on an object's motion is gravity. And so that's what we mean by influence. Okay? What are some other ways that objects can be influenced? Well, we just said that they can be influenced by gravity. They can be influenced by, so I'm going to name some stuff that we'll talk about much later in the course. They can be influenced by things like magnets. They can be influenced, objects can be influenced by the phenomenon of electricity. But the biggest way objects can be influenced is by things that we would consider verbs. Objects can be influenced by a push. They can be influenced by a pull. They can be influenced by being thrown, or by being kicked, or by being launched from something. They can even be influenced by being held in place. So notice that a lot of these, other than gravity, magnets, electricity, and this is not an exhaustive list, there are basically an infinite number of ways that an object can be influenced. There's an infinite number of ways we can describe this. But notice that a lot of these are verbs, okay, other than gravity, magnets, and electricity. You push something, you pull something, you throw, kick, launch, hold something, okay? All those are verbs. All of these influences on an object's motion, we have a name that kind of means all of that. We call them forces, okay? And that's the title of this unit. This is the forces unit. The technical definition of a force is a push or pull. Everything can pretty much be boiled down into a push or pull. A push or pull on one object resulting from its interaction with another object. I'm going to underline two important parts of this. Another object. Geez, I can't write today. A push or pull on one object resulting from its interaction with another object. That is key here. It is really important that you understand that forces arise from an interaction between two objects. Okay? Forces don't just happen because of one object. It's an interaction between two objects. In a little bit, we'll talk about how to analyze the forces on a particular object. You should always be able to tell me what two objects the force acts between, what two objects the force is an interaction between, if you're going to analyze that particular motion. Okay, you should always be able to tell me, okay, well, you're saying there's a force on object A. From what other object does this force on object A arise? Okay, that's very, very important. So, forces are pushes or pull, a push or a pull that is an interaction between two objects. Forces are vectors because they have both magnitude, size, the size matters, it matters if you push on something just a little bit or a lot, and the direction. The direction matters as well. Okay? If I try to push a desk sideways, I get a different result than if I try and lift the desk up, or if I try and push it into the ground. The units of forces are newtons. Okay, that's what we measure force in. Newton is symbolized by a capital N. And we'll talk a little bit more about how we get the unit of Newton later on, but it's not important for right now. The thing with forces is, an object usually has many, many, many different interactions with all different objects. Okay, there's many, many forces on any object. So in order to help sort out all of these forces, what we do is we draw what is known as a free body diagram, or an FBD. And the point of a free body diagram is it's sketching out all the forces on an object by writing them as if we're doing tail-to-tail vector addition, which is why we just learned that in the last video. So we're going to practice a bunch of free body diagrams right now. Again, what we're going to do is we're going to write out the steps here, and as we write out the steps, on the back you'll notice that there are a bunch of situations we're going to do the steps. We're going to write down those steps as we actually carry out those steps. Okay, so the steps for drawing a free body diagram. Step number 1, after you read the problem and determine that you should draw a free body diagram, you will draw a dot to represent your object. Just a dot, a very simple dot, not a sketch of the object, just a dot. And you label it, the dot, with the object's name. So, if we were to look at our first example here, we'll get to this part in a second. Our first example is a basketball that is in projectile motion. So, the basketball is my object. First up in my free body diagram, so I'm going to draw a dot, and I'm going to label it with the object's name. This is a basketball. Okay, there we go. 3 seconds, we've already got the first step done. Step number 2 is to draw an axis to indicate the positive x and the positive y directions. So we've actually done a little bit of indicating positive x and positive y directions already in the kinematics unit, where we said that, especially when we got into free fall and projectile motion, you have to define what you want to be the positive direction and the negative direction. That's going to be the same here. We want to define those directions. What are we going to say is positive? What are we going to say is negative? It doesn't matter what we pick to be positive or negative, but we do have to be consistent. So in this case, I'm going to draw my axis off to the side, and I'm going to draw it like this. This is kind of what I call the standard axis, although, again, you don't have to draw it this way. The standard axis has x to the right and y pointing up, kind of just like on your normal graph that you see. And I put a little plus sign in there to indicate that these are the positive directions. So that's step 2. I have an axis drawn. So step 1, dot with a label. Step 2, draw your axis. At this point, I have already taken care of at least half of the problem. Okay? If you don't do those 2 things, you will not receive full credit from me. It takes 5 seconds, but you have to do them. Now we're going to get into the actual process of doing the free body diagram, the important physics stuff. Step 3 is when we're going to start drawing our forces. We're going to represent all forces with labeled vectors. Now, I hope you left some room down here because there are some rules for drawing these vectors that we're going to go over now. Rule 3a. Okay, how are we going to draw this vector? All right, to represent a force. All these vectors that you're about to draw, they start on the object, so on your dot, and they extend in the direction of the force. Rule 3b is that especially if a question asks for a scaled free body diagram, then if you know that one force is bigger, you should draw a bigger vector. The vectors should be scaled to match the magnitude of the force. Even though we're not going to see this today, I'm going to do Rule C, and I'm going to tell you about diagonal forces. A diagonal force is a force that doesn't show up in the x or y direction. It's kind of in an in-between direction. If you have a diagonal force, what you must do is you must split it into components. We're not going to deal with any of those today, but we will see them in the future. They are coming. Rule D you are, when you're doing a free body diagram, to draw the forces that are exerted on your object, not the forces exerted by the object. People run into trouble with this when they start thinking about the forces that the object puts on other objects. Once you've got your object drawn and labeled, you're considering only the forces that are put on that object by other objects. You're not considering what is put on what that object does to the other objects that you're not drawing free body diagrams for. Okay? And then last but not least, rule E, 3E, objects can't exert forces on themselves. Okay? You can't have an object that exerts a force on itself. The reasoning for that might not be really clear right now, but basically what this prevents is it prevents objects from causing themselves to accelerate. It has to be an outside external force that causes an object to have its motion be changed. So let's apply these rules to our free body diagram. Here's our basketball. It's in projectile motion. Remember what we said about projectile motion. That means that the object is in free fall, which means the only influence on it is the force of gravity. Which, by the way, where does the force of gravity come from? Okay, gravity itself is not an object. If you said it comes from the interaction between the basketball and the earth, you're absolutely 100% right. So, the basketball, if it's in projectile motion, if it's in free fall, we know the only influence, the only force acting on the basketball must be the force of gravity. So I'm going to draw a vector starting on my object and extending down in the direction of the force. And I'm going to write out that this force, I'm going to label it with F of gravity. So it's a big F and then as kind of like a subscript, gravity beneath it. Okay? Now, just because an object has forces on it does not mean that it will automatically be in motion. Okay? Whether or not an object is in motion and what type of motion it has depends on how all of the forces add together on the object. In this case, we're only dealing with one force. Okay, so it's a pretty good bet that this object will be in motion if it's not already. But there might be a situation where we have 2, 3, 4, or more forces acting on an object. So it's not just that we're looking at each of the individual forces. We need to look at how all the forces act together. In other words, we need to find what is known as the net force. Net here just meaning total or sum. Okay? Matter of fact, the definition of net force is the sum as in SUM, of all forces on an object. We look at the net force in the directions given by our axis. So it's going to sound a little like we're going to have to do trig here, but we don't right now. We might in the future. We split our net force into components. All that means is we split it up into x and y directions. Okay? We discussed the net force in the x direction as well as the force in the y direction. And again, the reason we do that are these directions do not affect one another, typically. So, for this example where we have our basketball, we need to talk about the net forces. So I'm going to write F net for the net force, and then I'm going to put a little x beneath it. So F net x, the net force in the x direction. I don't see any forces in the x direction. The x direction in this case was to the right. That was the positive x direction. To the left would be the negative x direction. But I don't see any forces in those directions. There's only forces in the negative y direction here. So I'm going to say that the net force in the x direction is 0 newtons, 0 little capital N. The net force in the y direction, however, is not just going to be 0. I'm now going to look for the forces in the y direction. There's nothing in the positive y direction, but there is a force in the negative y direction. That would be the force of gravity. So I'm going to write the net force in the y direction is F gravity, but since it's in the negative y direction, I'm going to put a negative sign in front of it. All the negative sign indicates is the direction. It doesn't mean the force itself is negative. That doesn't really make sense. It's just there to show you the direction. If you had a positive force, you would make that if you had a force in the positive y direction, I should say, you would not make it negative. You would leave it as a positive variable. So it would be plus F gravity. But that's not the case here. So we have the net force in the x direction is 0 newtons. The net force in the y direction is negative the force of gravity. Let's look at some more common free body diagrams. You right now sitting in a chair. You're probably sitting in a chair right now reading this. So let's draw a free body diagram for you. First thing you do, make a dot, write a label, U. Now we're going to make an axis. Let's do our standard axis. No reason to change it. We'll talk about reasons why you would change your axis later on. Okay, y up, x to the right. Both of those are positive. Now the force is on you. Okay, now what is influencing your motion? Very clearly, you're not floating away. You're not floating off into outer space because gravity is affecting you. The force of gravity on you from the earth affects you. So I'm going to draw an arrow down. And again, write F, gravity. However, you're not in free fall. You're very clearly not in free fall in this case. There is something else affecting you, and it happens to be the object that's touching you, the chair. So, how does the chair influence your motion? It stops you from being in free fall. It stops you from falling down. That means that the chair is actually pushing up on you. So, I'm going to draw an arrow, a vector, in the positive y direction, and we're going to call this F, chair. I don't think there's any other forces. You're not being pushed or pulled to the left or right at all. So now again, it's time to write our net force equations. F net x and F net y. Okay. F net x, again, there are no forces in the x direction, so I'm going to call that 0 newtons. In the y direction, I have a force in the positive y direction, F chair, so I'm going to write that down. It's implied that there's a positive sign in front of it. There's also a force in the negative y direction, F gravity. So I'm going to write that, but again, it's going to get a minus or a negative sign in front of it. So minus F gravity. Okay? You can think of this as being plus a negative F gravity or as just being minus. Okay? Either way, there's a negative in front of that force because it's in the negative y direction. That's it. Right now, all we're practicing doing is writing our free body diagram and then writing our net force equations. You can't have one without the other. If you're going to write net force equations, you have to have a free body diagram. And if you've drawn a free body diagram, you'd better write some net force equations. Next example, a tire swing hanging from a tree. Tire swing. There's our object. Here's our axis. X, Y, plus. So, the tire swing. Again, the tire swing, I'm imagining, and you've all seen a tire swing or just a regular swing. They hang straight down. They don't just float around because of the force of gravity on the tire swing from Earth. So again, we're going to write a downward force, negative y direction, F, gravity. Now, what holds the tire swing up? Because, again, it's very clearly not in free fall. Well, it's probably attached to a rope because it's hanging from a tree. So, we're going to say that the upward force is the force F, that's what F stands for, of the rope. F net x, as it has been in the past, there's no force in the x direction, so that's 0 newtons. It's not always going to be that. Matter of fact, the next two examples, the net force in the x direction will not be 0, but in these cases it is. F net y, F rope in the positive y direction, F gravity in the negative y direction, so it's minus F gravity. Okay? 3 fairly straightforward examples. Now, let's look at forces that are in, let's look at a situation where we have forces in 2 directions. A person pushing a heavy box across an icy, frictionless surface. So what's our object here? It's not the person, but it's the box. Okay? We'll keep our standard axis. X, Y. Now, the box is on the surface. It's very clearly not floating away. It's definitely affected by gravity. F, gravity. Okay? We also have that box, no, I wouldn't say it's resting on a surface, but it's in contact with a surface, okay? And that surface makes it stop being in free fall. That icy surface keeps it from falling and being in free fall. So I would say that icy surface exerts a force upward. So you can call this F from the ice, or you can call it F from the surface. It doesn't really matter. We're going to learn the technical name for it in a few days, in a few videos. For right now, it is fine to just call it the force from the ice, directed upwards. There's one other force on this. A person is pushing this box. Even though it doesn't say it, let's imagine that they're pushing it to the right. That would mean that the force, F from the person, is exerted to the right. When I go to write my net force equations, I now have a force in the x direction. There's no force in the negative x direction. F person is in the positive x direction. So I'm just going to write F net x equals F person. And in the y direction, I have F ice in the positive y direction. Notice that what I write down here is exactly the same as what I write up here. So you can't call this F ice and then go and call this F surface. That would be wrong. I don't want that. F ice minus F gravity. And there's your net force equations in the x direction and in the y direction. If you want, try and do this next one on your own. I'm going to fill it in silence. Okay, there we go. So, as you can see, we have 4 forces this time. We labeled our object box, and we have our x and y axis. Okay, then the positive directions are indicated. Again, gravity is pulling the box down so it's not floating away, but the floor is resisting that. The object's resting on the floor, or at least it's in contact with the floor. So that means that the object is not in free fall, it's not falling down. So the floor must be exerting an upward force. The person is pushing the box, we'll say, to the right, and there's lots of friction between the floor and the box. So what we're going to assume that means is that friction, and this is a good thing to remember, always resists motion. So friction tries to resist the motion of the object. If the box is moving to the right, because the person is pushing it to the right, then friction acts back to the left. Okay? Friction always opposes motion. So in the x direction, the net force is F person minus F friction, minus because that's in the negative x direction. And in the y direction, we have F floor minus F gravity, minus because gravity is in the negative y direction. Okay? There's a quick intro to free body diagrams, net forces, and why objects move. We're going to continue building on this as the unit goes. But this is crucial. You need to know how to write free body diagrams, and you need to know how to draw free body diagrams and how to write net force equations. There's going to be more to it, but we'll cut it off there. Okay?